string a bunch of exclusive orders together, and it's even or odd number of ones. Odd number of ones, 1, even number of ones, 0. Right? Questions on the second page. Then some of those rules of what was similar to redundancy and complementary. The general rules being A, X, or 0. What is A, X, or 0?
A.
Put that one first to give you that false sense of security that everything's going to work out just like or. And we had A or A, X, or 1. A, X, or 1 is not A. So if A is 0, the statement is true. If A is false, excuse me, the statement, if A is true, the statement is false. If A is false, the statement is true. That's the opposite value of A. Now we start to see that exclusive OR is a very weird operation. Then we have A, X, or A. By definition of exclusive OR, if the values are the same, the answer is
0, 0.
false. Yeah, 1 or 1, 0 or 0 with exclusive OR, false. And then A or not A, which essentially boils down to definition. When the two values are opposite, exclusive OR is
1.
1 or true. Okay. So those are the techniques you're using here. If you have an OR 0, you can essentially ignore the 0. If you have an OR 1, that's going to swap the value. 17 is a good example of this. There's 3 answers here. Why?
It's 3 variables.
Well, it depends on what I exclusive OR 1 with, right? I can either exclusive OR with it, the entire thing, or just one of those individually, and that's what I showed for my 3 answers. You could have taken C XOR 1 and gotten C naught, or you could have taken B XOR 1 and gotten B naught, or you could have taken A XOR 1 and gotten A naught. Really work many of these examples. Any that you want to see work through?
Can you do 19 for example?
Okay.
That's 16.
Just make sure I'm reading that right.
One of
AB, XOR C, XOR AB. Is that C naught?
Correct.
XOR C naught. So exclusive OR is commutative and associative. That means I can move the terms around in a way that's convenient for me, or I don't have to physically move them. I can combine the things that would be meaningful to combine. What would be meaningful values to combine?
AB and AB.
AB, XOR, AB.
So you give the 0.
that would be 0. AB XOR AB would be 0 because if they're the same, they're always 0. Both 1 or both 0. Okay. And then, of course, we have the C XOR C naught, which is always opposite, therefore 1. This one right here. XOR 1. Everything's an XOR, so those two are going to have an XOR between them. 0 XOR 1 is equal to 1. It's simple. Simply exclusive OR two values, and it's just pick one. If you string together more than one exclusive OR, it's actually pick an odd number. 1 is also an odd number. That's true with that definition. You're just rearranging them in such a way that you apply one of these rules because exclusive OR is commutative and associative. Others? Is an interesting result. This is what we're going to expand on, I think today. Get to this. There's a couple of different ways to approach this. You have all of these ABs. One way to approach this problem is to say AB naught XOR AB naught is equal to what?
We're assuming 0.
0. Why are you assuming 0?
You have to pick them. They're the same.
They're going to be the same. Yeah, at all times they're going to be the same. Doesn't matter if they have a naught or not. If they're the exact same, XOR is always going to be equal to 0. And thus the first answer. AB XOR CD XOR 0 is equal to this first answer. But you get an interesting result if you combine it in a slightly different order. Let me rearrange this just to emphasize that. If I did AB XOR move over one of the AB naughts, XOR CD XOR AB naught. And I instead combine these two. AB XOR AB naught is equal to 1, always opposite. That gives me 1 XOR CD XOR AB naught. Now I can pick and choose because exclusive OR is commutative and associative. And if I take this one XOR the AB naught, what do I get?
Just be AB.
It would just be AB. Yeah, by this first rule and the double naught rule, right? That would just be AB, get that same answer. However, we get an interesting result if we instead combine these two. 1 XOR CD would be CD naught XOR AB naught. Why is that interesting? Well, that's because it's the same as, oops, extend that far enough. That's the same as CD XOR AB. Is that correct? Assuming we didn't do anything wrong. But that's a bit odd, right? This is different than what we got with ands and ors. That would be like saying AB is equal to A naught, B naught. Is that true for and? No, those are not equal. A or B does not equal A naught, or b0. But what this problem implies is that is true for exclusive OR. So I'll take, which one am I on, 16, B16, got it? We're going to continue working with that page. Oh, there's one more page, sorry. Getting ahead of myself. Oh, the review stuff here. Kind of a mess. Make sure we got the same there. I'll cue up that handout I had for you last Friday. Big long answers. Kind of hard to read, sorry. I had a lot of standalone cells in our Karnoff maps. That turned out very poorly, didn't it? What does that say? Should have just written it on different lines so I could have larger. So the last term is supposed to be A, B naught, C, D naught. A, B naught, C, D naught. It's this box right here. So there's nothing above, below, left, or right. All by itself. Now, got it?
You guys can pass it down this way. Alright. You can. Good. Is it rich? You got it. There should be. If not, I'd probably have one in my backpack somewhere. It should be by the staplers.
I'm going to continue chipping away at these. Again, these represent proposed rules for exclusive OR. They're not all true. You reviewed the first four. Those are those rules over here. 5 was, is that true or false?
True.
True. It is commutative. Exclusive OR is commutative. This is the associative rule. Is
True.
exclusive OR associative? Yes. True. Can we do 7?
No.
Is it distributive?
We edited there, but yeah, it looks like distributive. That looks like it's true.
So to test if this is distributive, we would need a Karnoff map, A, B, C. Actually, not a Karnoff map, truth table. 0, 0, 1, 0, 1.
Can you see if it's true just by distributing it on the top? Or no?
Well, this is a circular argument. The only way you can distribute is if that is true, right? Just by distributing it, that doesn't, just because you can do it doesn't
Right,
mean
doesn't mean it's true.
legally can do it, right? And that those two are equal to one another. Yeah, I mean, this is really unique. Part of the reason I like to talk about exclusive OR is because you don't very oftentimes get introduced to a brand new operation, right? This is the kind of things that we take for granted, right? We should be able to distribute. I just did it, right? Well, you can't assume anything with a new operation. You've got to test everything.
Right.
But by filling out this truth table, we'll quickly get a sense as to whether or not this is true or false. Right? Filling out truth tables, what would be easiest to start with to fill out this truth table?
Zeros and ones.
Yeah. Zeros and ones, specifically for what variable?
A.
A, right? A would be the easiest place to start, because if A is 0, the
Okay.
expression is 0, has nothing to do with exclusive OR, and 0. Exclusive OR doesn't produce anything weird, right? So the answer there is going to be a 1 or a 0. So anything and 0 we know to be equal to 0. So that's easy. If A is 1, then it boils down to whether or not the exclusive OR is true or false, right? So BC
0,
is 0,
1.
1, 1, 0, and 1 is just going to produce that same result. Okay. In the distributive form, A, B, X, or A, C, what is the value of the first 4 rows of our truth table?
0.
0. Why?
Because A is
So
0.
A is still 0.
A is 0, 0 and anything is 0, and A 0 XOR 0 is 0. So if those are both 0, first 4 rows are the same. Well, if A is 1, then we need to check what's happening with B and C.
Right.
So if A is 1, B and C are 0, what do we have?
0.
We have 0 XOR 0, which is
0.
0. If B is 0, this first term is a 0. C is 1, A is 1, we have a 1, therefore
1.
same thing here. A is 1, B is 1, so I have a 1. C is 0,
1.
therefore is that 1, sorry.
1. Yeah.
And then everything's a 1, I'm going to have
0.
Good job here, did I?
Nope.
Yep. Everything's a 1, I have 1 XOR 1, which
Equals
is 0. So true or false?
True.
True. I can distribute an AND across an exclusive OR. What is 8 about? Yeah, it's more distributed, right? Can I apply the FOIL process,
Yeah.
essentially? If you can distribute, then yes, you can FOIL. All the expansion of distributing will then be true. The reason that is I can just treat this as an individual factor and distribute that. So this now I can prove, because this is true, I can prove this by other means without going back to the truth table. So I can distribute the A, X, or B. So that would be A, X, or B, and C, X, or A, X, or B, and is it D?
Yeah.
D, okay. Because the distributive property is true, and then because the distributive property is true, I can go through and distribute those. I have A, C, X, or B, C, X, or A, D, X, or B, D, and then by the fact that it's commutative and associative, I'll have the same things I have here. AC, AD, BC, BD. Just different. So yes, I can apply all the rules of distributing that we've done both with ands and ors, and you may have done in other algebra classes in the past. 9. True or
Are
false?
you allowed to do the slash?
That's what this is all about, right? 9 is how does De Morgan's law work with exclusive OR? Okay. What exclusive OR kind of points out is that operations aren't really binary, right? There's not just 2 operations. We can think of there as 2 more operations. So is the opposite of exclusive OR and? I don't know. Let's test to see if this rule is true or false. Let's try a truth table. 0, 1, 1, 1. A, X, or B, not. Okay. So normally the truth table for exclusive OR is 0, 1, 1, 0. So A, X, or B not would be 1, 0, 1, 0, 0, 1. Is that the same as
A not, B not.
A not, B not?
Let's see.
Well, when is A not, B not true, or when is it false?
It's only true when there's 2 ones.
Yeah, so A1 and 1 is true. That happens with 2 zeros, right, because of the not. So this would be 1, 0, 0, and then 1 and 1 would be 0 and 0, therefore 0. What's the conclusion?
Yeah.
No,
False. Big X through this one. Well, maybe, I don't have it on the sheet, but maybe the opposite of exclusive OR is regular OR. So maybe this is equal to A not or B not. I don't have it on the sheet, so you probably can guess what the answer is going to be. 0 or 2 zeros, that means I have 1 or 1. 1. I have at least 1 0, therefore my answer is 1, 1. There's the only place where it's 0. Are those the same? No. Okay. How about 10? Is the opposite of A, X, or B A not, X, or B?
Let's see. 1, 0, 1.
Yeah, so the not changes this to 1, so I'd have 1, X, or 0.
1.
True. 1, X, or 1, therefore
0.
false. 0, X, or 0. 0, X, or 1. 1.
It is true for that first
And then, is that the same as doing A, X, or
B not.
B not? Yeah.
I'm gonna say yeah.
Yeah. So I have 1 as 0, X, or 1. True. 0, X, or 0. False. 1, X, or 1. False. 1, X, or 0. True.
That is true.
So this is true. Something else new with Boolean expressions. The opposite of exclusive OR is exclusive OR. It's sort of an opposite of itself, which is really bizarre. Or it's another way of thinking about why this is true. Nots change 1s to 0s and 0s to 1, right? So it just inverts the value.
Right.
Why is inverting 1 the same as inverting the whole thing? There's 2 kinds of operations with exclusive OR, same or opposite. Inverting just one value changes same to opposite. right? And changes opposite to same. So flipping just one value is the same as flipping the entire expression. It's not a rule on this page, I don't believe. Let's have it further down. But how does that then expand? Suppose I had A, X or B, X or C not. So if exclusive OR with multiple operations means what? Even or odd, right? If there's an odd number of ones, it's true. If there's an even number of ones, it's false. Changing one value switches even to odd, or odd to even. So I can switch just one of these values, right? So this would be equivalent to A not, X or B, X or C, which would be the same as B A,
or B
X
not,
or B
or
not,
C.
X or C.
A, X or B, or C not.
Or
A, X or B, X or C, 1, X or 1.
sure, you could do something like that, but I was thinking of this.
Yeah.
Why does that do the same thing?
It's technically just it's an opposite again, but it's everything is opposite.
Yeah, so if I had an even number of ones, my answer would have been 0, so the not should switch it to a 1. If I have an even number of, what did I say, an even number of ones, and there are 3 terms, even number of 1 leaves me an odd number of zeros, right? So the only way with 3 that I can have an even number is 2, right? Or 0, I guess. We should include the 0 as well. But if I have 2 ones, I have 1 0. So flip those around. 2 zeros and 1 1 now makes 1, the opposite of 0. Or if I had an even number of ones in that there were 0 ones, that's 3 zeros. Therefore, switch them all. I've now swapped the expression. Okay. So I can swap any one or swap all 3. In general, De Morgan's law would be invert an odd number of variables. 1 is an odd number. 3 is an odd number. Okay. So I could swap any combination of an odd number. Thus, the problem we were just thinking about, it actually might be on here somewhere. Yeah, number 16. Is 16 true or false?
True, true.
True. Because there's an even number, swapping an even number maintains the same answer. Because if I have an even number of terms and an even number of ones, an even plus an even is an even. So I have to have an even number of zeros. So swapping everything around, changing all my terms, actually doesn't change the answer. 16 is sort of the opposite case of what we're learning with De Morgan's law, that if I have an even number of terms, swapping them all keeps everything the same. If I have an opposite number of terms, swapping them all actually gives me the opposite. Kind of confusing. So 16 is true. Myself back. The way things were. That. All right. 12, 11. and 12. 11 is absorption for exclusive OR. Can you apply the absorption rule for exclusive OR?
Truth table.
Hopefully you've been fooled enough by exclusive OR to say, I don't know, I have no idea. Okay, this is a completely new rule. I can't assume anything from OR. Maybe it will carry over, maybe it will not. All right. So what do I do if I want to check?
Truth table.
Truth table. All right. Let's check if absorption works for exclusive OR. 0, 0, 1, 1, 1,
11.
A, X, or
X or AB.
B versus A. Well, I know what A looks like. That's 0, 0, 1, 1. What do I get? 0, 0, 1, 1.
Let's try it. 0 so 0 is 0.
So if A is 0, I'll have 0, X, or
0.
0, and anything is 0. So this is going to be false. This should also be false, right? Because I'll have
Right.
0 and 1, which is still 0.
Right.
So far, so good. If A is 1,
1 and
1,
0,
X, or, now B is 0, so this is equal to
0.
0,
So equal to 1.
which is true. And then 1, X, or 1 and 1 is
1,
1, which is
0.
0.
They are not equal.
They're not the same.
False.
Cannot apply. Absorption is unique to the combination of and or. This is false.
Big time bet.
What is it equal to? And after looking at the truth table and sneak and peek at number 12, you could possibly guess what it is equal to. When do we get a truth table where everything's 0 except for A is 1, B is 0?
B not.
Maybe not, right? The only line where we have a true statement is A, B not. These two are the same, right? A is 0. B is 0 here. Only time this is true is here. The logic explanation to this is when you only have 2 items, exclusive OR means pick one. So imagine I'm going to give you a prize, and that prize is, you only pick one. You either get $10 or you get $10 in a brand new car. Okay. Which one do you want to pick?
No, isn't it brand new?
$10 a brand new car. Nope, you violated the rules. You pick both. Okay? So you can only pick the A without the B. Okay? It's a trap.
Right.
I'm trying to trick you into sort of violating the rules so I don't have to give you anything. So even though you really want the $10 in the car, you can only pick one. Getting the $10 with the car is picking both because your other option is $10. Therefore, you can only pick the $10. Seems like a legal loophole, right? Lawyers get paid big money to write statements like that so that they can trick you. So it's sort of a more extreme version of the absorption law where you really can't pick both. You can only pick the A without the B. How about common identities? Does common identities work the same way with exclusive OR as it did with regular OR? Again, the answer should be, I have no idea. Well, let's test. Put together the truth table for A, X, or A naught, B. You should already know the truth table for A, X, or B. True or false?
It's the world. First one's 0.
0.
X or 0. Equals 0. X or 0. 1, 1. X or 1. 0, 1. X or 0 times b, 0 is 1. They are not.
They're not the same. Even though both of these cases, there's just one row difference, that's enough. They have to be exactly the same before you can say they're equal. So A naught B, that's only true if A is 0, B is 1, that happens here. Then the left-hand side is just what's happened with A and B. And then you're applying the exclusive OR rules. Same false, different true. They're not the same. However, we've seen a truth table like this before. What truth table gives you 0, 1, 1, 1? A or B. These are the same. When both 0, we get a 0. When either 1 or both is 1, they're equal to 1. Okay. So 13 is false.
14 is true.
14 is true. Let's think of the logical scenario for this. Same setup. I'm going to give you a prize. You can pick one of the two prizes. Either you can have $10, or you don't get $10 and you get a brand new car.
I don't get $10 and I'll get a brand new car.
So yeah, obviously the choice seems obvious in this scenario, right? That you take, how about I switch these around? You either, no, that's in here, we can do the same thing, right? There's such a clear choice between these two. How about you either can have $10 cash or no $10 in cash, but you get a $10 Best Buy gift card. Okay. Now this seems a little more obvious where you can play the game. So the question is, why is this the same as regular OR? That is, pick one, the other, or both. How does this exclusive OR change into regular OR? So you either get $10 cash, or you don't get $10 cash, and you get a gift card. $10 in gift card.
It's the same value.
So the trick is, you take the $10 cash, okay? Say, I'll take the $10 in cash. Then, by default, you didn't not take $10. So if this is 1, this becomes a 0. And therefore, this is false no matter what you do with B, right? So you take the $10 in cash and say, well, I did not take the $10 in cash, so now I want to take the gift card because this is going to be false no matter what. Therefore, I've picked just one. Right? It's kind of a weird little loophole in the way exclusive OR works. Again, it kind of looks like what we do with common identities. We knock out that A naught, but what changes is our XOR changes to regular OR. This appears to be very different than absorption. However, in my mind, I think of it as almost being the same. It's just a stronger version of absorption. It's not that this isn't needed, it's this one can't be picked. Therefore, I have to take the A without the B. Just an extreme version of absorption. Only can take that one on the left, that shorter term. So I have to explicitly say, I do not get that other choice. Look at the homework problems. Just noticed an error. If you already printed this off.
It says 16 and it says
Yeah,
17.
so 16, it should be 17.
Right.
You got that?
Yeah, I looked at it, I was like, no, 16, did I put
Yeah,
the
'cause
wrong one?
I tried to open it and I said, oh, did I open the wrong one?
Right.
And I didn't change the name of this either. So this should be worksheet 17.
Right.
I called this XOR simplification. My file name's correct, 17 XOR simplification. I just didn't change the name. So largely this gets at this absorption version of exclusive OR and the common identity version of exclusive OR. So the first couple just apply the rule, just different letters. B XOR AB. What does that become?
Do you like have to use a truth table to figure out these mostly?
Nope. So the idea is we want to generalize the rule. So let me get rid of the truth tables just to summarize this whole mess. So what the absorption rule for exclusive OR says, logically, it's a trap. If you pick this one, you've necessarily picked both.
Right.
So you have to pick the A without the B.
Yeah.
The common identity version of exclusive OR, this is a loophole. So in terms of awarding a prize, this is a trap. Can't pick the one with the extra stuff. This is a loophole. Pick this one, then this is necessarily false. Therefore, you can go ahead and pick the B no matter what you do. This side is false. So this is a loophole, so it actually is you get one, the other, or both. So no, we don't want to go through the truth table every time. We want to generalize these rules. And again, I initially start with just different variables. So B XOR AB.
A not B.
A not B. Yeah, I have to take the B without the A. Okay. The only one I can pick is this one on the left. I can't pick any B, because I can't take this one because it comes with that trap. Excuse me, I can't, yeah, because it comes with, can't pick this A because it comes with the trap of also getting B.
Number 2 would be A, B, not C.
A, B, not C. Good. This one just expands it to multiple variables. I have to take the A, B without the C. If I take the one with the most amount of stuff, I've necessarily chosen both, and therefore the statement is false.
A, B, C, not.
3 takes it a bit further. Say, yeah, I mean, that's just applying the rule directly, and then you can do a little bit more with it. 4 is expanding this notion, doesn't work with the not operation, and yes, it does. Satisfying these rules just happen at a different point. The C, you pick C not when C is actually 0. When you don't choose C. So applying this, generalizing this rule, what is 4? It's the same trap. If you choose this first one,
Right.
you necessarily have chosen both sides. Therefore, you have to take the C not
A, not C, not.
without the A. A not, C not. Not, C not. I have to take this one and explicitly ban the other one. I'll let you try 3 on your own. Let's look at the next set. They kind of get us exploring the generalization of this rule, this common identity version. So just different letters. A, C not, X, or C. What does that become?
Would that just be A not? Because it'd be A not or 1, right? A not X
So
or 1.
it's similar to this, right? We have C, the second rule there. It's similar. We got C all by itself, and C not's repeated.
Right.
So that's this rule here. So it works the same way as exclusive or excuse me, common identity, except my XOR changes to OR.
So it's A or B? No, A or C.
A or C. Okay. So you knock out that C naught, XOR changes to regular OR. Multiple variables, B naught, XOR A, B, C.
It would be
B
A,
not.
C not, or E. Yeah, or
A.
A not, C not.
A, B
plus
not.
B.
So it works just like regular exclusive OR, where the B naught knocks out the B,
A
except for
or A or B or C.
except for you change the exclusive OR to regular OR. Summertime, I think we have a little bit more to say about this worksheet, so we won't officially collect this on Wednesday, so you can hang on to it until Friday. I think we have a bit more practice. We're getting started. Give these first couple of pages a try. We'll continue the discussion on Wednesday.
Alrighty.